Thank you. And let me share my screen. So, good morning, everyone. And let's start for the second practical work part. And firstly, I would like to invite you to find the guidelines for the second practical work part on the autos. And I already downloaded it. So the second practical exercise, we will talk about the binary amplitude shift key signal detection with noise. The purpose is to solve the problem with the symbol detection when comparing received single level with the threshold, and we also need to study the binary amplitude shift key modulated signal. And the report also, similar with the previous report, we also must contain the following: and the objective, and your for source code, and your plots, and your conclusion on noise immunity comparison for the rectangular pulses and the binary amplitude shift key signals. And we have 9 tasks, and we can separate them into some like 3 parts, and the first and the second task, so we can do it together, and the after the left we can also separate do like third or fourth and do it together. And now we can see the first and the second task. So we save a copy of the first practical exercise and set parameters to work with the unipolar rectangular pulses. And now we still need to draw the transmit signal, receive the signal, and detect the signal. Let's move to the octave. And please open your first exercise code. And here is my first exercise code, and I will open a new script and save it as the second practical work. For the BASK. So, and in the first work, practical work we did for the last task is to the convert single to the non-return zero, and we just need to copy first part. We generate the single sequence, and here we put it back. Don't forget it. Which will be the task 1 and the task 2. And also, we still need our single and the transmit single, and here is compilation. So, and don't forget load the communication component here. And for the single noise ratio received here. Threshold, and we need here the non-return zero and the its threshold. And detected a single. So let's come back here. So the first task is the first practical exercise, which we are required working with the non-rated zero single, and here we need to come back to the unipolar single. So we have to convert the single level from the because we already have this one and the plus one and the minus one, and when we need to come back it to the 0 and 1, and the threshold will the less and to be come back to the greater, and we don't need this convert single to the noise non-return 0, and we also need to change back from the threshold. And also we will use other like representation options like a subplot, and it has the 3 components, which means the m, n, k. M means the number of the row, and n is the number of the columns, and the k is the number of the each figure. So if we want to plot like this, we will get the m equal to 3, n equal to 1, and the k will be the first, the second, and the following. So here is our code, and which will looks like this. So let's do it. And tx, and we can put it here because this is NRC and the thinner like 20. So threshold here, and so we can subplot. And for the 3, 1 and 1, and first we plot the transmitters and read on, and labor, which will be the time. Y label, don't forget it. Single ST, and second picture will be here. We just change it as this 2, and now we need to plot the threshold line. So here we can use this one. 0 to the length as x. Good down, and threshold to, and don't forget, can give his color will be the red. Don't need labor, and just hold it on. Hold on. So And the second picture we can put it together with the threshold, and it will be the received signal. Time units and change the Y label. So the last plot will be the detected SD. It will be the SD. Save it and let's write. Some problem here, and let's check it. SD. Hold on. Oh, wait, I forgot to change here for this. Run it again. Oh, now you can see the three picture. They stay for the first, second, and the last. For the first is the transmit single, and the second picture will be the received single, and the last picture will be the detect single. And 0 will be the threshold if the threshold minus, then the threshold, and it can be the, we can save it as the detect single. So this is the non-return 0 code format. Now we hope we need to change it to the unipolar. We just don't need this one. Command it, and we change the threshold as the big one. Let's write again. So, and you can see the threshold is changed back to the 0.5, and here this will be the first will be the transmit single, and the last picture detect single, and our signal set for the 20 is quite high, and so they have no errors here. Let's change it as like -5. So you will see a lot of uh, the receiving single will combined with lots of noise, and the detect single also have lots of errors, and it's quite a bad result. So we need to the more advanced method. So let's move to the third task, and we observed by the analyzing detection accuracy for the different signals ratio, and there are some certain points where the detection has been performed incorrectly due to the too strong noise, like we just performed. Um, and the example of the such occurrence is showing the next picture. Here is the receive single. I think his single noise ratio much higher than mine, because mine is quite bad. So we can change the threshold, and here we will use the average value can be our threshold. The idea is the averaging is based on the adaptive nature of the noise, and here we have the received single, and we will use the transmit single plus to the noise. So we can do some mathematical expectation. So, and use this uh, formula formula. So we can let the noise to be the 0, And here is the example, transmit single plus to noise single, and it should be has a better performance. And uh, before we do it, and here the chronic multiplication will be the similar with the previous part, and we just need to we we just need to know here we use the mean value of the received single, change the threshold. So let's do it. And the third plot will be like this. And threshold which to the here, and we will need to some no threshold. We can add some more component like we specified the n will be the number of the symbols. We count the s elements as is here. We have 10, so the next will be the s. And m will be the 100, the samples per symbol. And our received single will be our received single will use the upsample detected data. We use the chronic the multiplication. So the we should reshape the single into the segments to the each column. So the SX received single we must reshape it. So n will be the row, m will be the column. We just reshape it. Yes.
So yes, I'd like to add some comments here that
Okay.
what we currently are doing is we change the shape of our signal. So our signal is one sequence of numbers, yes, which consists of 10 information bits. Each of them has been repeated 100 times. So now we slice up that signal into 10, which is n, 10 pieces, yes, and arrange each such slice as a single row of matrix. For that purpose, we use a function called reshape. We specify in this reshape original vector. We specify dimensions of our new matrix which we'd like to have, which would be 10 by 100. And this way, this matrix will have 10 rows, one symbol in each row, and 100 samples per each symbol. Yes, so that's what we are doing here.
Thank you. And let's go. And so, and which we must change we use the mean value here. And we still need to use the chronic to upsample to the chronic multiplexer to upsample the detector data. So SD with the ones.
So yes, and here we do like by calculating mean over each row, we accordingly change 100 numbers into one number, and Kronecker multiplication here again repeats each number 100 times so that we can plot it in our last figure. Yes, so this is basically only needed to draw a beautiful picture, nothing else.
Yeah. Yes. Here will be the task 3 and the task 4. So, but for the transmit single, if we want to plot it, and it will change the list. No, receive single. We did the change for the matrix, so it couldn't plot it, and we need to put it in our received single. Will be the key here. So, and let's do it right. And here will be the new threshold and the transmit single, and with a very bad single noise ratio, and we still can recover our received single. And let's check here, and almost here is 1 0 0 1 1, and no no errors here, and we can increase it as like the single worse saturation. Let's write that again. And you can see here the last part will have the mistake. So the transmit single will be the 0, and the received the detector single is the 1. So, and here also have the mistake for the transmit the single is 1, and the detect single is be the 0. So, but it will be the performance will be the better than the previously threshold. Let's come back to the guidance, and the result will look like this one. So first we will try different single noise ratio value to observe, and you will see which method, how it will change, and which method will better. So the task 5, and we only run for the like 10 symbols, and here we will increase to the 10,000 symbols here, and we will define the M-matrix here. And here we will calculate the errors here. So, and we will use the relationship operators here, and we can find any mismatch. Therefore, the operators here should be used. And here you can see the transmit single symbols here, and the first 25 symbols here, and the detect the symbol here. We can combine, compare it, and find the mismatched. Use this formula, and it will be error. We will generate the error vector here, and we calculate the number of the errors here. So let's do it. Just close it.
So yes, for this last picture, I'd like to also mention that please take note that in this particular example, when we had minus 10 decibel, this means that the noise is stronger than signal 10 times. So noise is much stronger than signal, and anyway, we only had 2 errors out of 10 symbols transmitted. So this was much better than without averaging. Yes, so this helps indeed.
Okay, so let's do it. And the task 5. Here we will increase to 10 to the 10,000. And received, and we do not change the here for the float, which single threshold. Next will be the 1 point here, a little bit change. To the 125 clarification with the M. So the M is the here, increase here, here, we put it here, and will be the columns here, and here we also add here subplot. Now we will means received subplot.
So this way we only show first 25 symbols out of these 10,000 because we cannot really show this many symbols
Yes,
in
yes.
hope to read something from the plot. So we only show 25 first symbols.
We denote arrow, and the arrow will be the here. That's D. Where equal to the S. Then we can calculate the number.
So yes, again, I would like to add here to the logic of this command. Basically, this error vector is the result of comparing your original data S and detected data SD. And the only thing here is that I see probably we need to move that before Kronecker multiplication. Yes. Because S only had 10,000 symbols and SD will after this. So yes, not equal command generates accordingly 1 per each mismatch. And then on the number of errors, we basically calculate how many of one symbols do we have. And this will be the number of errors. So this will generate some statistics for us to answer how often the errors are happening.
Yeah, so let's write. Yes, for my laptop will cost some time, I think.
But you can speed up the process if you put the semicolons after each command, especially when we have these 10,000 symbols, yes? And I can see that, for example, line 19 is not finished with semicolon, and this output actually is what takes this long time. This printing on screen is taking so much time, but the command itself works very fast. So you can put the semicolon after the end of line 14, line 19 to avoid this output, because we don't really get much from this information which is printed on screen. So many numbers and we don't really understand each of them.
Yes, but how can I stop it?
Control C stops execution.
Here, and we
and you need to put semicolon after those lines. So if you don't have semicolon, the result of command is being printed into this console. So you can see that in line 14, yes, you don't have semicolon, and also you don't have in 19.
So
you just press semicolon, yes. No, symbol semicolon, yes. Like the end line symbol.
Please, I will give you control and
Okay.
how to get your.
I see. I can press button request control. I will request. Okay.
Okay, thank you. And you help me.
So yes, basically what you need to do is to put a semicolon here, yes, at this symbol, like here. And this way it will prevent it from the output. And also here. Okay. So now it should work much faster.
Oh, yeah.
This is the specifics of MATLAB and Octave, that outputting to the console is actually happening very, very slowly. And we can, too many signals we can see.
Yes, we can see the values here, the workspace, and we will see the number of the arrows here, which will be the 553. And for the arrow vectors, we can plot it, and looks like, yeah, a lot of the numbers here.
So this gives better idea out of 10,000 symbols how many were actually received incorrectly. And it turns out that a little bit more than 500 of these 10,000s were incorrect. So much more often, even with this bad signal to noise ratio, we still receive data correctly.
Yes, we still can change it for the single noise ratio as -5, and yes, but on the workspace and the US is the total number of the arrows will only have the 24, and it's quite better if you compare it with the previously similar results. So let's move to the here to move to the sixth task, and we will use the modulation tab with the binary amplitude shift key. So here will be the possible single is with the sync and which will be transmit the 1, and the 0 will be the 0. So we will add the harmonic carrier symbol, and it will looks like this one. It's multiplied here, and we can note here the high arrow count, and it's more than the 50. So let's can do it our case. And we just add the harmonic carrier single before the here. Yeah. Let's take before the chronic multiplexing. Will be the S1, S0. And we give the frequency as the 20. So our transmitted single will use the S chronic multiplied with the S0.
So yeah, you basically consider that you have changed the carrier. Previously, our carrier was just a level of 1, and now we have a harmonic signal instead of level of 1.
Yeah. So sooner we can calculate as like 10. Let's try. Column 5, 9, 14. Oh, mistake. And you can see here with the received signal and the S.
I can see that
with,
your
yeah,
first
here.
and third plot for some reason looks not like pulses. Something is amiss there. So let's have a look. Rx is maybe some.
Here I forgot to add here this one. The first 25.
Yes. Yes. So yes, that's missing. And the last one also, yes. And the last plot also needs this. Okay, now it's everything correct, yes?
Yes. And here we'll the a binary amplitude shift key single, and we can see uh, the definition here. If the Z1 transmitter will be the sync wave, and the 0 transmitter here will be the 0. So it will look like this here. Transmit single with the 1, 0, 1, 0, 1, and so on. And our received single also with the noise impacted with here, and the with no 0 will dynamically get around the threshold will be the 0, and the one single will be uh, multiplied with the carrier single as the 1. So here will be the detector single, and you will find here still has some mistake. And here we have the 0, and here we can be considered as the 1. So let's see the total mistake here with around the 5,000. So it's seen with the guidelines here, and more than 50.
So yes, I would have a question for you. How would you explain why we have improved signal to noise ratio from -10 to +10, and for rectangular pulses we had like how many 500 errors, yes, and here we now have 5,000, which is half symbols are with errors. Why this happened? How can you explain it?
Yeah, I think uh, the single noise ratio will be the impact factor.
You can try change it. Let's see.
Yeah, like 20. So let's see here. Oh, still has the
It didn't
5,000.
help, so it doesn't have to do anything with signal to noise ratio. And the reason is why in this case averaging doesn't help is that actually if you look at the signals, you can maybe show them right now. Yes.
Yeah.
So the sine wave average value is 0. right? So if we take this piece where the signal happening, if we calculate the average value, it will be 0. And the 0 is also average value for, well, that 0 level, yes? So they are, for average level, indistinguishable. Both 1 symbol and 0 symbol has 0 average value. So average approach cannot work with harmonic signals. It only worked with pulses.
Yeah. So is the problem still will be the threshold, and or we need or we need to do the some change of like we need a more advanced receiver part function. So let's move to the next task 3. We will do the we will need to use the optimal receiver, and it's kind of the coherent demodulation. So we will as our received signal to multiply it with the here as 0 with the pure carry signal. And if you see here, and the threshold will be the here noise single and the carrier single, and it will like the threshold here will be the 25, and for the 0 and it's around 0, and it's the threshold the detect single over to the 25 and will be considered as the 1.
So yes, please
Yes.
don't be alarmed if you don't completely understand right now this receiver. This is actual receiver which is being used in practice, yes, and we'll talk about it much more in our lectures. We will have separate practical exercises only for that part. So right now we only need to understand that there is such a method which is actually being used, and to see how much better it will work if we use it instead of averaging for harmonic signals. So it's not a bad sign if you don't really understand how it works now, because it will be explained to you later.
Yes. So, and the new threshold will be the value of the half energy, and we will change here, and we will use the received single to multiply it with the S0 here. So let's do it. And so in order to here we will use the we will add one more picture here. So I plan to uh, here like and threshold, we don't put the threshold on the received single together. So we hope to add a separate threshold, what will looks like. And here we will, and here after the chronic multiplication, I will calculate the like x we compared with the S0 multiplied with the S received single here. So we will add the one more picture. We change the 3 as the 4 here. And pop here. And the third picture will, I think, will be the XX. We'll see the here. And hold on. What will look like? Hold on. Y label, and we call it Y label. We call it detector before the discrimination. we add the final with the detector plot. So here will be the false and D. Hold on, and the line disappeared, and we see here. God, here's the
So if
yeah.
I understand correctly, you wanted to show this integrated signal, right?
Yeah. Yes. Yes.
But there is no integration still made, yes? In the formula, there was an integral sign, and under the integral, we had S0 multiplied by SRX. So we need to actually make some integration first to show it. And well, this is a little bit tricky, but I still, if you think it's interesting to observe, we can actually try and make it. Maybe you can show, or maybe I will rather try request control and maybe see if I can help you here, because currently right now I don't also have ready solution. I just can to see.
Yeah. Threshold, I forgot to change it.
Yes, threshold too.
Yeah. We will use the sum. And here will be the S0. S0. So we just want to label transmit the signal detector before threshold 4 here. Great. One. Here, yes, for no more things here. How to say? We just copy here. Come back here. That's from here. 3. And will be the XX threshold around. Maybe it will run and try it. SK 05. Some mistake names of the K. Put it here. Some threshold real. Hold on. Secondly,
Wait, actually, let's see. Here, yes, we generate vector with length 25 multiplied by m, and then we find the length of this vector. Well, it can be simplified by just placing there 25 multiplied by m, yes, which will be the same, basically.
okay.
So, but the problem is with some. Is that my microphone? So much noise. Okay, so the problem here is well, one more thing.
Oh yeah,
that
here
we
is
actually
4.
didn't change.
And 4, 1, 2, and 4, 1. So
this is some sort of problem with file name, looks like, but why wasn't it happening before?
Yeah.
Is beyond me.
Can
Again,
see. We just copied. Right. Threshold here. Some. Okay.
so if we do that
Yes.
in that file, probably it would also work. Yes, because well, it shows some mistakes which are not really telling where is exactly mistake. So yes, let's see if we try. Sorry, if we try and do it here. Where would that happen? Yes. So will this file run also if you correct this bracket mistake?
Yeah.
Or it will also again tell that there is a file name problems or something like that.
SD. So SD will be the.
Yes, it's basically the same, but will it work? That is the question. If I see, it was complaining about file name. However, the error was in this bracket. So sometimes these errors are, well, not real, not showing where the problem really is. So what now we would like to see is that actually what Tianhua Chen tried to show you was this signal, this integrated signal, yes? And in order to calculate it, we need to this integration. So let us try and do this, let us say so, on the fly, because this wasn't in the task and you don't really necessarily have to make this, but well, let's try and do this. So first of all, I'd like to see where is the workspace. And in the workspace, your signal XX is just 10,000 symbols. So at this step, we are already too late because the integration has been already calculated and we have final result. What we'd like to see is actually how we add first number and second, then we add third number, fourth number, and so on. Here, however, we have the total sum of already 100 numbers. So let us change a little bit our code here to multiply our signal. So wait a minute, please. Let us try and do this signal as, I don't know, maybe some XX capital. And use a function called repmat. Repmat accordingly replicates this certain column or certain line. And for example, I'm going to replicate XX and repeat it 10 times to make 10 rows of this XX signal. So basically, this way, I'm going to stack it vertically. I have forgotten to put this semicolon. Okay. So yes, now I have, you can see that I have replicated this matrix 10 times. So why do we need to do that? We need to replicate this S0, yes, to be actually the same as this SRX. And so let's wait a minute, this SRX. So for this reason, we need to replicate it 10,000 times. So that would be, let us denote it with S0. Right now I'm trying to explain logic how I'm going to do this. So later we'll be able to use it in our code repmat. So we replicate signal as 0, but it is a row vector. We need it to have as a column vector. So that is why we transpose it here with apostrophe sign. Okay, now it is a column vector, and we are going to replicate this entire column as a one row and n columns. So now we have this as 0 as with the same dimensions as reference. Yes, let's see if it's correct. So yes, S0 is a sine wave in the column. So now what we are going to do is actually add that in our code. So before this, I will accordingly say that I have S0 as rip mat and S0 small transposed one column, one row and columns, right? So, and here now we are going to multiply them element-wise, not as a matrix, because here we had a column vector multiplied by the matrix, which accordingly was conducted according matrix multiplication law. Now we multiply matrix and matrix element-wise, so therefore we put this special dot product notation. Yes, so this means that actually first element of first matrix is multiplied with the first element of the second matrix, and then we calculate cumulative sum. So cumulative sum actually, so command window, consider we have sums n from 1 to 10, yes, and we'd like to see how they grow how they grow after being integrated. If we calculate the sum, it will be just the sum of all these numbers, which is 55. But what we want to see is how we gradually get to these 55 step by step. Like, for example, at the beginning we have 1, then we had 3, 6, 10, and so forth. This is called cumulative sum. Accordingly, this shows integration process. Yes, how it gradually starts from 1, adds up next number, and ends with the total sum. So this is what we are going to do for our signal here. Cumulative. Yes, and the result needs to be converted into the single vector. So I'm converting it into the column vector in order for it to be plotted. So let's see if it will. Yes,
Yeah.
now everything works correctly, and you can see this integration process. Again, we will talk about this much more during our next lectures, but for now, since there was such an interest, we also included this picture here as well.
Yeah. So here we see the here it should be the one, and the detect single has some problem here. That's the one. Yeah, it should like this one, and
But it
let
was
me check.
working previously. What happened
Yeah,
to it?
but here I can see the detect single or the 0.
Yes, indeed. So let's see what's the problem.
Yes, here's some problem here. Yeah, here I forgot to change here for the S0. Here there will be the correct. So let's try it again. Yes. So here and here our transmit single and with noise, and the sync wave will represent 1, and you will see the before the threshold. We can see the threshold as here as around 25, and if they can do the discrimination, and if this close, because then the threshold and can be considered as a 1. So here as 1, and here we have the very lower the threshold and can be considered as the 0. So, and almost there is no mistake here, and we can check the errors here will be the 0, and here our single noise ratio will be the 20. Now we change it like -5, how it will looks like here. Yes, and here some mistake, and we can see here close to the threshold, and transmit single will be the 0, and here be considered as the detect single be considered as the 1.
Yes, so this is actually where these errors come from. You can see that because of the noise, we are above threshold where we shouldn't be. This is happened because of the noise, yes, and this leads to incorrect detection.
Yeah. And we can check the errors here. So the total errors as the 200. So it's quite yeah, it should be the smaller than previous the unipolar method, and maybe you can try more different thing or to observe. You will get your own result and your conclusion part. And that's all. Thank you for your attention for the practical work part. And we should don't forget to submit your practical work part. Thank you.
So thank you. Yes, thank you as well for interesting presentation and for good practical exercise lecture. So this concludes today's lecture. If you have any questions, you can ask them. If you will have these questions later, you can send them by email. If something is not working, you are always welcome to contact me or Tianhua Chen. We will be glad to help you. So yes, thank you, and we'll see you next week then. Thank you.